Okay, so we're going to have a look at a video on using Avogadros law to work out the formula of a hydrocarbon using combustion calculations. So we'll just have a very quick look at Avogadros law. Slight variation over here. Avogadros law, essentially, sometimes called also Avogadros principle, tells us that 1 mole of any gas, if it's at the same temperature, always has the same volume. So we're going to look at it here with regards to 1 mole of any gas has a volume of 24 decimeters cubed at 298 kelvins and 1 atmosphere of pressure. Okay, so as far as at AS level chemistry, that's pretty much what Avogadros law means. Now please don't get Avogadros law mixed up with Avogadros constant, which is the number of particles in 1 mole of anything at 6.02 times 10 to the 23. They are kind of related, but they're different from this context that we're going to use here. So what does this mean then? Well, it means essentially that if I have 1 mole of solid, okay, we're used to using mass equals number of moles multiplied by the RFM, and we know that for the RFM or solids this is generally a variable, so this changes depending on what the actual substance is. However, so therefore the number of moles of something is dependent on what the RFM is, okay, so they're not directly proportional. Now, if I apply this law to gases, okay, so the number of moles of a gas, okay, is equal to the volume, okay, and I'll put that in decimeters cubed over 24, because 1 mole of any gas has a volume of 24 decimeters cubed, whereas 1 mole of any solid has a mass which depends on its RFM. Okay, now therefore the number of moles, okay, is directly proportional to the volume. So if I know the volume of something and I know the volume of the volume of two gases, well then I can tell the moles ratio of those two gases to each other. So for example, let's say I had O2 and I knew that I had 100 cubic centimeters of that, okay, and I knew that carbon dioxide, let's say I had 300 cubic centimeters of that. Well, to work out moles of this, I would take that and I would divide it by 24. I would change that dm cubed to cm cubed now, to 24,000. And to work out moles of this, I would take 300 and divide that by, of course, 24,000. Okay? Now, because the 24,000 is constants in both, my ratio of this oxygen to carbon dioxide will come out at a 1 to 3 ratio. Therefore, if I know the volume of, in this instance, oxygen and carbon dioxide, I would also know the ratio of moles of those two things. Okay, and that's really the principle that we're going to apply here in order to work out the formula of a hydrocarbon through combustion. So we'll start out with a couple of really simple ones. Good idea if you have a calculator and maybe a periodic table with you. Okay. You can pause. I'll do some examples. You can pause the video, of course, and check that those are right. Maybe a good idea to write down Avogadros law and perhaps these two formulas, which I'll wipe off the board very soon, okay, because they'll be useful as well. Okay, so you might want to pause this video now and maybe jot those down, okay, and then I'll start. Okay, so if we look at something really very simple, just to begin with. So we have a question here where we've got to work out the formula of a hydrocarbon, so we'll just call that HC. Okay, and we're going to combust that hydrocarbon in excess oxygen. So if we combust that hydrocarbon in excess oxygen, we will get carbon dioxide and we will get water also. I'll just move that because it's... Okay, so we would get carbon dioxide and water made. Okay, so the examiner tells us that we start off with 100 cubic centimeters of that, okay, and the hydrocarbon is burnt in 500 cubic centimeters of oxygen, and it tells us that at the end of that 50 cubic centimetres of the oxygen was unused. And as always, I'll write in the info, all the info that the examiner tells me. Now I can very quickly tell that therefore 450 cubic centimetres of that was indeed used. The examiner then tells me that we had 300 cubic centimetres of carbon dioxide was made, and we had 300 cubic centimetres of steam made. Now, the water is not always as a gas, so you need to read the question carefully, because sometimes it tells you that everything was done at room temperature, which would therefore tell you the water is a liquid. Okay, and if it's a liquid, we say that its contribution to the volume is insignificant, and we count it as basically being zero. And we'll cross that bridge when we come to it. So the question is, how on earth do we now, this is a very simple one, how do we get the formula of the hydrocarbon? So in order to get the formula, we need to know how many hydrogens there are and how many carbons there are. Well, remember earlier we said that if we've got the volume, and I showed it in that first little calculation, if we've got the ratio of the volumes, then we've got the ratios of the moles. So this is 100 to 450 to 300 to 300. So that tells me one of those must react with 4.5 oxygens to give me 3 and 3. Okay, so that's the hard bit done, to be honest with you. Now, of my hydrocarbon, the only source of carbon on the left is from the hydrocarbon, and on the right is from the carbon dioxide. So therefore, the 3 carbons that are here have got to come from 1 mole of this, so B must equal 3. Over here, the hydrogens in the water, the only source of hydrogens on the left are from the hydrocarbon, so there are 3 times 2, which is 6 hydrogens, so A must equal 6. So my hydrocarbon must have a formula of C3H6, so it must be propane in that instance. Okay, so that's a really nice, simple example, and that shouldn't cause you too many difficulties. Okay, so I'll do another one or two like that. I'm not going to dwell for too long on this type. I want to get stuck into the slightly more complicated ones that you will also have in your notes. Okay, so if we have a look at the example, so I'm just on your notes here now. If we can should blow that up a little bit, hopefully you can see it. Okay, so I'm going to look at this one here. We have 10 cc's of a hydrocarbon, required 30 cc's of oxygen. Okay, to combust, 20 cc's of carbon dioxide was formed at room temperature. Now the first thing you might notice about this one is there's no mention of water. So I said earlier at room temperature we would assume that the water has 0 volume. So let's move that to the notes. We'll try and keep it sort of on the board here if I can, so you can look at it while I do it. Okay, so again I'll write it out in the same way that I wrote the last one out. So I've got HC, hydrocarbon plus oxygen, okay, gives me CO2 and H2O. Okay, so I've got 10 cc's of the hydrocarbon, I'll just put that in. I've got 30 cubic centimetres of the oxygen it reacted with, doesn't say anything about the oxygen being in excess this time. And I've got 20 cc's of carbon dioxide which was made. So again I've got my moles, my volume ratio, which means essentially I've got my moles ratio. So I've got 1 to 3 to 2. So I can work out from one of these, the carbon dioxide, the carbon could only have come from here, so therefore my carbons in my formula must be 2. But what about my hydrogens? How on earth do I get my hydrogens this time, because I've got no volume for my hydrogens? Well, if we look at the oxygen, we have 6 oxygen accounted for in total on the left hand side. My carbon dioxide accounts for 2 times 2, which is of course 4 of the oxygen, so I have 2 oxygens going missing from the left to the right. Therefore I need 2 waters, which gives me my 2 oxygens. So B, or my number of hydrogens, must be 4, so my hydrocarbon must have a formula of C2H4. Again, that would be considered to be a pretty simple, straightforward one. Right, we'll have a look at this. this second one here, okay, and then we'll move on to ones that are maybe a little bit trickier. So I'm going to zoom out there so we have a little bit more room on the right hand side here to do the calculations. So again, we'll write out the equation. We'll write hydrocarbon plus oxygen goes to, let's write carbon dioxide and water, like I prefer it that way. Carbon dioxide and my water. Okay, so let's go back and see what information is it that the examiner has given me here. Okay, I'll try and fix the light in here a little bit. Okay. Right, so let's have a look. We have been told that we've got 20 cc's of the hydrocarbon, so we'll put 20 cc's in there. 70 cc's of the oxygen was required, so we've got 70 cc's there. 40 cc's of that was made, okay, and we made 60 of that. Okay, so it couldn't be easier, to be honest with you. So we have 2 to 7 to 4 to 6. My hydrocarbon has got, so my number of carbons in it, carbons equals, got 4 here, hydrogens equals 12. Now this is where we need to be careful in this one, because we have got 4 carbons and 12 hydrogens, but they're split over 2 molecules of my hydrocarbon. So my hydrocarbon is not C4H12, it is actually C2H6, so it's half of those values. Alright, so we just needed, the trick of this one was just the 2 that the examiner had given us there. Okay, right, we'll go and have a look at, let's this one here. Okay, so we've got 10 cubic centimeters of a hydrocarbon exploded with an excess of oxygen. There was a contraction this time, which is different, so we'll deal with that in a second, when the product was treated with a solution of sodium hydroxide. And again, that and that, both those things are different. Okay, we haven't come across those before. There was a further contraction of 30 cc's when I added it through sodium hydroxide, deduced the formula of the hydrocarbon. All of them are at room temperature and pressure, so they're all at the same temperature and pressure, so therefore Avogadros law applies. Right, so what is the implications then of this sodium hydroxide? Well, if you remember, we'll just use this one down here as an example. When we combust anything, it did say up here that we had an excess of oxygen, so our products will be carbon dioxide and water. Now, sodium hydroxide, you should know, is an alkali. The only substance in here which would react with an alkali, if you remember maybe even from hard water GCSE, is carbon dioxide, which forms carbonic acid. So carbon dioxide is an acidic gas, and that will react with my sodium hydroxide. So what information can I therefore in my question up here take? If it tells me here when the product was treated with sodium hydroxide there was a further contraction of 30 cc's, what they're telling me there is that I had 30 cc's of carbon dioxide. Okay, now let's go back here and we'll deal with the other information. Okay, so I'll just zoom back out again, so we've got a little bit of room to sort of do a calculation. Right, so again I'll write the equation. So we'll write CH plus O2 goes to CO2 plus H2O. Let's fill in the info we got. So we got 10 cubic centimeters of that. Okay, we had an excess of oxygen. We had carbon dioxide, we know, is 30 cc's. It tells us that everything was done at standard temperature and pressure, which is 20 degrees. So, like I said earlier, therefore our water will not be steam, will not be a gas, okay, and will be of 0. Right, so we've got 2 unknowns here that we've got to somehow get in order that we would be able to work out the formula of our hydrocarbon. So it tells us, and this is important here, it tells us there was a contraction of 30. Right, now, we made 30, okay? There was a contraction of 30, so therefore our original volume must have been a total of 60, okay? Now, 10 of that we know was our hydrocarbon, so we must have had originally, I'll just write down that, 10 must have been our hydrocarbon, so therefore the other 50 that's missing here must have been our oxygen, must have been 50 cc. So if you think about it, if we had 50 cc's of that, and they reacted fully together, and that's a total of 60 cc's, and we had a reduction of 30, or a contraction of 30 cc's, well then that would bring us down to the 30 there and the 0 for the water. So we've pretty much broke the back of this now. So let's fill in our information. So again, we've got one of these, which is good, because we just, whatever number of carbons and hydrogens we have over here, we know they've come from one molecule of this. Okay, so we've one of these, we've got 5 oxygens, we've got 3 of those, so we've got to get our waters in order to work out how much hydrogen we have. So again, we have in total on the left hand side, on this side, we have 10 oxygen atoms to deal with. Down here we have balanced 6 of those oxygens, so in other words we've got 4 oxygens missing, so we've got to put a 4 there in order to get our oxygens. Okay, so we now know that we have 3 carbons, so C3, we have 8 hydrogens, so therefore our compound must be C3, write that down here, C3H8, okay, and that would be the answer to that particular question. Okay, so we'll do another one like that, and then I'll do a couple slightly harder, not that they're harder, but the wording in them is just a little bit different. Okay, and again, you can pause the video and maybe have a look at it. You've got all these in your questions anyway. Okay, so let's have a look. We'll have a look at number 2 here. So we've got 10 cubic centimeters of a hydrocarbon. Okay, it's exploded again in excess oxygen. This time we have a contraction of 25 cubic centimeters. Okay, so we'll try and do this sort of at the side here if I've got enough room. So we'll go CaHB plus O2 goes to CO2 plus H2O. Okay, so we've 10 cc's of the hydrocarbon, and again I like that because that means we've probably got a ratio of this of 1 to something of the others. Okay, we had a contraction of 25 cc, so we'll just make a wee note of that. Contraction, we'll say that's contraction number 1. Okay, on treatment of the product with sodium hydroxide, we had a further contraction, so we have a contraction of 40 cc's, which is number 2, and I'll just write, because I like making sure we annotate our calculations as we go along. Okay, 40 cc's with the sodium hydroxide, we've got to get the values. So this is pretty much similar to what we've already done. Right, so we know that we've got 40 cc's of the carbon dioxide because the sodium hydroxide absorbs that. Now, if I have 40 of that and I had a contraction of 25 but I made 40 carbon dioxide, my original volume had to be 40 plus 25, which is of course 65. I have 10 cc's of that, so if it's 65 in total, I must have had 55 cc's of my oxygen. Right, so I can start putting in some numbers. I've got 1 there, which I wouldn't put in, but we'll put it in for. I've got 5.5 O2s, and I've got 4 here. 5.5 oxygens in total means that I've got 11 oxygen atoms. Down here I've got 4 times 2, which is 8 oxygen atoms, which have been accounted for. Okay, out of my 11, so I'm missing 3 oxygen atoms, so I've got to put 3 waters to get my 3 oxygen atoms. So I've got 4 carbons, and I've got 6 hydrogens, so therefore the formula of my compound is C4H6. Okay, So the other ones in this little exercise are pretty much a variation on that theme. I'm going to flick over to the next page. There's a couple which are maybe a little trickier. Alright, and we'll have a look at those, and we'll have a quick go through them. Okay, these ones you just need to be a little bit careful about the wording. Alright, there's a couple of words in them that the examiner or the question writer has changed, and they've just changed them a little bit, but they make a fairly significant difference to your question. Okay, right, so I'm going to have a look at this one, problem 4 first of all. So we've got 10 cc's of an unknown hydrocarbon. Okay, so again I'll write out my little equation at the bottom. A spark with 90 cc's of oxygen. Okay, so there's 90 cc's of that. Now note that that's excess, so that is not going to be a 1:9 ratio. When the resulting gases were cooled back to the original temperature, they had a volume of 70. Okay, so that's an excess, so my products must be that plus that. Okay, now, so we have got volume 7, exposure to the gases, sodium hydroxide. Now, this is where we need to be careful. Reduced the volume to 40. Our other two questions said reduce the volume by a certain value. This has reduced it to 240, so we need to be very careful there. Okay, so we've got to find the formula of the hydrocarbon. Right, so the first thing that we've got to do then is to realise that we've got 10 cc's of this spark with 90 of that, which is in excess. Alright, when the resulting gases were cooled back, they had a volume of 70. Now, if they had a volume of 70 when they were cooled back, that means that the water was contributing nothing. Okay, so what do I have left in here when I've got talking about my 70? Well, my 70 cc's is oxygen, which is in excess. There must be some oxygen in it, and there must be carbon dioxide. What is 0? This is 0 because the oxygen, or the hydrocarbon is 0 because the oxygen was in excess, so there'll be no hydrocarbon volume contributing to this 70. Exposure of these gases to sodium hydroxide reduced the volume to 40. So it was 70, it went to 40. Well, that must tell me, therefore, that I have 30 cc's of carbon dioxide. And the common mistake that we'll get here is people will see sodium hydroxide, and we'll see 40, and we'll put 40 in for the carbon dioxide. So that tells me that I have got 30 cc's of carbon dioxide in there. Okay, now if I have 30 cc's of the 70 was carbon dioxide, that means that the rest of it must have been unreacted oxygen, which means I have 70 minus 30, which leaves me that 40 cc's left over. That must have been unreacted oxygen. Okay, so I've got that, so therefore the oxygen that did react must have been 50 cc's. Okay, so I can now start putting this information together. Okay, so I have one of those because it was 10. I have 50 of oxygen must have reacted. I have 30 of carbon dioxide which was made. Okay, I have 10 oxygens on this side. I have got 6 oxygens accounted for on that side, so I'm missing 4 oxygens in other words, so I need 4 there. I've got one of these has 3 carbons in it, so it must be C3. Okay, and I have 8 hydrogens. One of those had 8 hydrogens in it, so C3H8 must be the answer. Okay, right, we'll have to go with one more. Alright, and then hopefully that will allow you to be able to do these on your own. Right, again we have a hydrocarbon. You can see the answers to these, by the way. You can use those. Unknown hydrocarbon was sparked with 100 cc's of oxygen, which again is in excess, so there'll be some of it left over. The resulting gas is cooled to the original room temperature. So there's excess oxygen, so I'm going to get carbon dioxide and water as my product because it's complete combustion. Okay. Again, I'll put in what I have here of that, 10 cc's. When they were cooled back to the original room temperature, so that tells me that water is not contributing to the volume, they had a volume of 75. So that 75 can only be oxygen and carbon dioxide. Okay, the oxygen is in excess, so there can be none of that left over. Volumes are measured at room temperature, so there can be none of that. Okay, and they had a volume of 75 cc's when they were cooled back, so that is both of those. Exposure of the gases to sodium hydroxide solution reduced the volume, and note, reduced the volume to 35. Okay, so if it reduced the volume to 35, that must mean there must have been 40 cc's of carbon dioxide, and the 35 that was still a measurable volume of gas must have been unreacted oxygen. So it reduced, so that was unreacted oxygen, so the amount of oxygen that did actually react must have been 65 cc. So be careful there. That's the oxygen in there that is not reacted. Okay, so we can now start putting in numbers. So we've got our 1 there. We have got 6.5 O2 there. We've got 4 there. And we can work this out now. Okay, over here I have 6.5 O2. So I have 13 oxygens in total on the left hand side. Over here I have 4 times 2, which is 8 oxygens. Okay, so in other words I'm missing 5 oxygens. Okay, so I've got to have 5 water molecules here in order to get those. So one hydrocarbon molecule has got 4 carbons in it, so C4, and 5 times 2 hydrogens is H10. Okay, so I've pretty much done a couple of all of those guys. Hopefully that helps you. Again, as I say, that problem 15 and problem 4 are both variations of the 2 problems that I did over here at the start, or sort of the middle of the video, but the wording is just a little bit different. So again, be careful of that, and don't get caught out from that point of view. Okay, hopefully that helps you work out the formula of a hydrocarbon from combustion. If not, okay, please ask.